Okay, here is the Chapter 5 review. Question number 1. What name is sometimes used to refer to the entire set of D block elements? Says right over here. The D block elements are metals with typical metallic properties and are often referred to as transition elements. We're going to call those transition elements. Number 2, which group on the periodic table contains the halogens? There's a couple ways that we could answer this. Here it says the elements of group 17 are known as the halogens, or here we are looking at the answer key to practice 1C way back in the beginning, and it tells us that halogens are group 17. So here is the answer to that question. Group 17. What are some of their characteristic properties? Well, it says they're nonmetals. They tend to be reactive. They tend to react with metals. And they tend to be gases at room temperature. They are quite a lot of different properties here. Let's say that they are reactive, they're nonmetals, and they tend to be gases. So, properties: reactive, nonmetals, they tend to be gases, and one more is that they tend to be toxic, right? They tend to be deadly if you breathe them. Fluorine's deadly to bacteria that cause teeth to decay, and so on and so forth. Identify the block period group and group name, if applicable, and element name for each of the following. So here's how we're going to do this. Each of these has an outermost electron configuration. We know that when they end in a particular outermost electron configuration, that's the block they're in. Block, of course, being this part of the periodic table. So here we are. We've got something that ends neon 3s2 3p1. Well, here's how we're doing that. If it ends 3s2 3p1, it must be in row 3, and anything that ends p1 is going to be in this, write that better, column here. So 3s2 3p1 is this guy. We'll say that's aluminum. So it's in the P block, it's in period 3, it's in group 13. There really isn't a name, and it is aluminum. And that's how we're going to do all of these. So here's argon that ends 3d10. Well, that's 3d, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be element 3d10 right there. It's zinc. So we're going to say it's in block D, it's in period 4, it's in group 12, doesn't have a name, and it is zinc. Here's one that ends P5, and it's in row 5, krypton 5s2 4d10 5p5. Ending 5p5 would put it right there. That's this guy, 5p5. That's our buddy iodine. So we're going to say that it is in block P, period 5, group 17, because it's, of course, in the halogens, and it is iodine. Lastly, one that ends 4f14 5d1. Well, the part that tells us 6s2 means it has to be here. The 4f's would fill next, and then 5d1 would be that guy right there. So 5d1 would be, we'll say 4f14 would have to be this guy, 71. Oh, let's see. How am I going to do this? Yeah, we're going to say 71 right there. That would be that guy. We don't know what its name is. We do know it is in, because it's ending D's, it's in the D block. It's in period 6. It's in group 3 because it's D1. Doesn't have a name, and it is Lu. That is, doesn't say. We'll say it's luthethium or something like that. We don't really care. We're just interested in the name. Okay, what is meant by atomic radius? Right here is atomic radius. We've got a table that shows us atomic radius right here. Atomic radius, atom sizes is our radius. The bigger the atom, the bigger the radius. So we'll say, what is meant by atomic radius? How big is an atom? What trend is observed across a period from left to right with atomic radii? Here's this table. And it tells us that as you move from left to right, the radius decreases. So we'll answer this question by saying, what trend is observed among atomic radii? We'll say they get smaller from left to right. Why is this? What we know is that the number of protons is increasing as we move from left to right. For example, potassium has 19 protons, calcium's got 20, scandium's 21, and so on and so forth. Get all the way here across to krypton, and that has 36. 36 protons pulls harder than 19. That means it makes the atom shrink because greater number of protons attract the electrons greater. So we'll say the reason why the radius shrinks is because a greater number of protons from left to right makes the atoms get smaller. What trend is observed among their atomic radii as we move down from a period from top to bottom? Let's remember that every time we move down to the next row, that's another energy level. Here in energy level 1, 2, 3, 4, and so forth. Well, energy levels means you're moving farther away from the nucleus. So, what trend is observed among the atomic radii as you move down a period? Radius gets bigger from top to bottom. Why is this? Each new row is a new energy level. That's why. What is electronegativity? Let's see what it says over here. Electronegativity. This guy right here is our table of electronegativity. Do we have here? Nope. Okay, let's see if we can find something about electronegativity. So a little quick Google searching tells us that electronegativity describes the tendency of an atom to attract electrons. So we'll say electronegativity is how much does an atom attract electrons? What makes fluorine special? A couple of things. One, fluorine is here on the periodic table. It's all the way at the upper left, and that means its radius is the smallest, and it is desperately trying to attract an electron because it is one away from looking like a noble gas. And that makes fluorine's electronegativity the highest on the periodic table. So we'll say, what makes fluorine special in terms of its electronegativity? Let me pause for a second here. We know that it is special because fluorine's electronegativity is the highest on the periodic table. Why is this? Because fluorine is the smallest. That means the electrons are closest to the protons and the attraction is the greatest. Also, it's really close to being a noble gas, and that makes its tendency to attract electrons huge because it's desperately trying to add that extra electron to turn its electron configuration from S2P5, which is that of a halogen, to S2P6, which is a noble gas. Okay, a bunch of stuff on ions over here. A couple of cute cat pictures I think I threw in here too. Where are we finding them? Here we go. Atoms lose or gain electrons when they're reacting. They become positive when they have one more proton than electrons. They become negative when they have one more electron than protons. These are ions when we have atoms that have lost or gained electrons. And so we'll say atoms that have charge would be ones that have lost or gained electrons. What's an ion? Let's say it's an atom that has lost or gained electrons. And this means that now they have a charge. They can be positively charged or negatively charged. It says here, what is ionization energy? Here's a little paragraph that tells us. Ionization energy is the energy required to remove an electron from a neutral atom. And so we'll say ionization energy is energy required to remove an electron from an atom. And here are two terms, first ionization energy and second ionization energy. It says the amount of energy required to remove one electron would be the first ionization energy. Therefore, the amount of energy required to remove a second electron would be the second ionization energy. So we'll say the first ionization energy is the energy required to remove the first electron. That makes the second ionization energy the energy required to remove the second electrons. Well, it says here, how does first ionization energy vary moving from left to right? And please explain this trend in terms of electronegativity. Here's what we know. Electronegativity is here. It's largest at the upper right corner and lowest at the bottom left. Why is this? Because everyone in this group is trying to lose that one electron while everyone in this one is desperately trying to gain one. So ionization energy increases as we go this way. It's also bigger when the atom is smaller, so it's going to increase towards the top. Smaller atoms pull harder. And so it says, how does first ionization energy vary moving from left to right? It increases. Well, why is that? Please explain this trend in terms of electronegativity. The greater the electronegativity, that means the greater the pull, the more energy is required to remove that electron. So ionization energy increases as we go from left to right. Here is number 8, and it says, please explain for each of the following, indicate whether electrons are more likely to be lost or gained. Alright, here's how we're going to do this one. This tells you exactly what is going on in each group. All of these elements are in group 1. All of these elements are in group 2. All of these elements are in group 13. This is 14. This is 15. Of course, this is still group 14. This is 16. And this is 17. It tells you that if you are in group 1, you have a tendency to lose one electron to become a positive ion. So we're going to say that elements in group 1 tend to lose 1. What is their ending electron configuration that would make this happen? S1. Here is group 2. Elements that are in group 2 have a tendency to lose because they form positive ions. How many? They have a tendency to lose 2 because their ending electron configuration is S2. Here are the elements in group 13. These are the elements in group 13. They tend to lose electrons because they tend to form a positive charge And because they're forming a charge of +3, they have a tendency to lose 3. That's because their electron configuration ends s2p1. Here is group 16. These have a tendency to gain. They tend to gain 2 electrons because they are 2 electrons away from looking like a noble gas, s2p4. Elements in group 17, like halogens, they have a tendency to gain. They tend to gain 1. We see this because they all have a charge of -1. They do this because they are 1 electron away from looking like a noble gas, p5. Well, where's group 18? That's these guys. That's these halogens, and we know that halogens don't really do anything. That means they don't tend to lose or gain electrons at all. 0, and that's because they have an ending electron configuration of noble gases, s2p6. Almost done. We're on the last page. Please arrange the following elements in order of decreasing electronegativity. This is easy because we know that fluorine is the most electronegative element on the periodic table. That means all we have to do is find these elements in order from left to right and from top to bottom. Okay, well, here we go. What we know is that fluorine is here, oxygen is here, carbon is here, lithium is here, sodium is here, rubidium is here. That means the electronegativity is going to decrease in this order. So, here is, obviously, fluorine is going to be the most electronegative. In order will be, next lowest will be oxygen, then carbon, then lithium. Now we're here and we're going down this group. Lithium, sodium, and rubidium are all in group 1, and they tend to decrease as we go this way. This one is asking us to list the elements in order of decreasing first ionization energy, and which is the hardest to remove an electron. Well, fluorine has got the highest electronegativity, so it's going to be the hardest. Obviously, oxygen's next to that, and of course, carbon is next to that. Then we've got potassium and lithium, which are in the same group. Well, they're all in the same row, except for potassium. So, the hardest to remove an electron is going to be fluorine. Then will be oxygen, then carbon. How do I know? Because fluorine's here, oxygen's here, carbon's here. Then we have lithium and potassium. Well, that means potassium is going to have the lowest first ionization energy because it's desperately trying to remove an electron because it has that stupid S1 configuration. So we'll say lithium, and then potassium is the next lowest electronegativity or ionization energy, excuse me. Sorry, there's someone knocking on my door and it was distracting. Number 12 is going to ask which trends in the diagrams at right indicate atomic radius, ionization energy, and electronegativity. Alright, well, let's do the atomic radius because we know according to this table here that radius is biggest in the bottom left and smallest in the biggest in the bottom right and smallest in the up. Sorry, someone's knocking on my door. Biggest at the bottom left, smallest in the upper right. We want a table, one of these basic ones, that is increasing from the upper right to the bottom left. That's this guy. So we'll say this table is indicating atomic radius. This other one is indicating ionization energy and electronegativity because we know they're greatest in the upper right corner. So this table is going to be talking about ionization energy and ionization energy and electronegativity. All right, everybody. Last one. The electron configuration of argon differs from those of chlorine and potassium by 1 electron each. Compare the properties of the elements such as atomic radius, electronegativity, and ionization energy. Well, let's get their electron configurations. We know argon is right here. Where's our periodic table? This guy. It's in the last group on the periodic table. It's a noble gas. It's in row 3. That means it's going to end 3s2, 3p6. We know that argon, let's write it out, has an electron configuration that ends 3s2, 3p6. Fluorine is one away from this in one direction. Actually, yeah. Fluorine ends 2s2, 2p5. We're not worried about the 2's. We're worried about the p6 and the p5. Potassium is 4s1. Here's what we know. Argon, not reactive. It's a noble gas. We know that fluorine, very reactive. Why? Well, we'll get to that in terms of atomic radius and electronegativity. Finally, we know that potassium, very reactive. Why? Well, here's what we know. Fluorine has a small radius, and it's desperately trying to gain that extra electron, and that means that it has large electronegativity, large ionization energy. That means it's desperately trying to grab an electron. That makes it very reactive. Argon, not very reactive. We're not worried about its radius or its electronegativity. It doesn't have any. But what we know about potassium is that it has a large radius, and that makes it have low electronegativity and low ionization energy. That means it's not very difficult to remove an electron, so it's very eager to react. That's all we're doing. All right, good luck on the test tomorrow.